science for data communication by transforming the message. We want to alter the message. So no, we're not going to alter the message, but then we want to send the message in the proper manner whereby someone cannot intercept and cannot alter or access the message that we want to send to the receiver. Okay, so goals of cryptography. So this is the main goal for the cryptography. We have the confidentiality, whereby the information or the message that we send, it should be accessed to those that we want only. So this is what we call confidentiality. And then integrity, whereby the data or the message that we send cannot be tempered or altered. We cannot change. I mean, whenever we got the message, we cannot change it. Okay? And then authentication. So authentication is for validate or verify the sender and also the receiver. And lastly is non-repudiation, whereby the sender cannot deny sending that message. So this is the goal for cryptography. And there are 3 types of cryptography. We have symmetric key, we have asymmetric key, and we have hash function. So symmetric key involve whereby we use the same key for encryption and also decryption. But then asymmetric key, we use a different key for we use 2 keys, one for public key, one is private key. And hash function is actually for us to verify the file integrity and also for us to store the password securely. Okay, so the terms that we maybe need to what we call to start with is plain text. So plain text is the original message that we want to send. It's either a text, audio, image, so anything. So that is what we call data. So this data, we call it as the plain text, the original one. Oh, sorry. And okay. And then ciphertext. Ciphertext is a message that we already alter, not alter, but then we already change into the one that we're going to submit into the channel. So this is what ciphertext is. Okay. And then encryption. So the term encryption is actually a process for us to alter the message. Okay, it's not totally alter, but then for us to hide the message. Okay, so the process for us to hiding the message. And decryption is a term where we reverse back the process, okay, to get the original message. Okay, so from plain text, we use encryption method to get the ciphertext. And decryption process is from ciphertext, we have the message that we cannot read, and then we decrypt, we use the decryption process to get the plain text, to get the original. Okay? And as I mentioned, we have 2 types of key, symmetric key or asymmetric key. And the algorithm will be implies to the key. The way we use the method for the key, we apply that our algorithm. Okay, so wait, I have a problem with my cursor. Okay. Okay, so we going back to chaos for to remind us the key features of chaos. First is we can generate a complexity and also pseudo-random. So with these features, it's had cryptography. We can have cryptography in terms of the key generation for the secure communication, and we can mask the data. So with these features is very important because whenever we get the random, because our chaos is random, so we got the sequence that is very random. So it is very highly chance for the attacker to get, to criminalize our algorithm. So because of this randomness, the higher possibilities not higher possibilities to get attacked, but then it's very high possibilities for them to get not get our message. Okay, and then for sensitivity to initial condition, so this is the features of chaos. So in these features, actually we can use for error detection and correction. So because of this sensitivity, we can check, the tiny error can be identified quickly. So then we can we can refine or revise the process immediately. So with this sensitivity, actually is very helpful in cryptography for error detection and also correction. So there are many practical utility that can be done in cryptography and IoT actually, because of whenever we talk about IoT, it should be very less computationally. Okay, it cannot have a it should be lightweight computational efficiency. So chaos algorithm can have this in this manner, whereby because whenever we have a chaos algorithm, the computational is very easy and it's not that heavy. So the efficiency of the computational is very good. So that's why the limited of these IoT devices is we can have this limited of IoT in terms of our chaos algorithm. And because of the sensitivity, we can provide strong encryption and also secure communication. And also we have to handle the hierarchical and decentralized network, which means we can make ideal for large scale in IoT network development. Okay, so this is just example. So because we are talking about the double pendulum yesterday, so actually because of this randomness of the system, the double pendulum system, it is very ideal for cryptography for key generation. And also double pendulum is very ideal to scramble the plain text to get the ciphertext. And also double pendulum can provide complexity without high computational for secure communication data. Okay, in double pendulum we have this deterministic nature, sensitivity to initial condition, and also randomness. So one of the good things to use actually double pendulum, especially for those who wants to study the energy. So it can reduce the energy usage. So whenever you want to transfer a data, so the energy usage can be reduced. So double pendulum is one of the best choice to be used. So this is just example of the how we want to use the chaotic system into cryptography. Okay, so I would like to highlight here where chaos cryptography is used for key generation and for secure transmission, and also I will also share with you how we use chaos into hash function. Okay, so let's take a look at the first example, whereby this one is a key generation. So as you know, in IoT network, each sensor need to use a unique cryptography key. For example, for a secure communication. So this is good for us to use a different key, so that is not vulnerable for the attacker. Okay, so the advantage of using the key generation, because we will have a large key space, and it is resistant to the brute force attack. And then yes, it is non-repeating because our sequence will be not repeating at all. So it produces an unpredictable nature. Okay, so where we can apply chaos key generation. So first we can use for secure device communication in IoT. We can apply in unique key for each IoT device, and also dynamic session key for secure transmission. Okay, so this is how. This is important because this is what you're going to simulate after this. First, you need to define the input. I mean, how we want to use the key generation for chaos. First, you need to define your input. You're going to have your initial condition and your key length. You need to know how long you want your key, and then you need to know what parameter you are going to use. And then you can generate the chaos sequence, and then the third one, you have to scale your chaotic values and normalize into 8-bit, and then you will have your key stream. So for example, in this case, we are using logistic map. So logistic map, we have R as our parameter, and we have our Sn. So I'm using this one for 10 iteration. Let's say I want to use 10 key generation. I want to have 10 key. So I'm just taking, this is just for a purpose of learning. So I'm just taking the first solution of X, and then we normalize the value. Okay, so basically in computer science we use 8-bit, so that's why I normalize to 8-bit, and then based on this one we will have our key stream. Okay, so maybe we can show how we found it, and basically the key generation we are using binary. Maybe I can show you one example of how we found the key. I also not remember. I mean, hopefully I am written some. No. Oh, this one is direct. This is just a direct. You have your X equal to 0.4, and then I scale value. This one, my scale is power of 6. So, and then I got 1 to 8 based on mode 256. Okay, maybe there is some that I can show, whereby you find the remainder. You find the remainder to get the value. So when you have 400,000 and then you find it in because you use the 8-bit, so your solution should be 256 in 256 mode. Okay, so this one is mode 256. So you find the remainder of this, then you can have this value. So it's just a matter of a remainder. Okay, you got it? Alright. Okay, so okay, so I mentioned I'm using power of 6 as a scaling factor. So my question is, what would happen if the scaling factor I change into a smaller or a larger factor? It depends on your solution as well. So what happens if I'm using a smaller factor? Yeah, that is very obvious. The key will change. Yeah, very obvious. Okay, so but then if you are using too small, for example, like power of 3. Yes, so that is very important. This is very important. So the variability of your sequence will be very less. So many repeating value will be there. So that will be not good. So that's why the scaling factor should be in the good term. Okay, so this would, the variability is less, means that our entropy range would be smaller, so that is not good. Okay, so our entropy will be reduced. But then, in fact, even as our friends mentioned, we change the key. So the strength of our key generation is also very low. But then, if we use higher, yeah, it depends. It depends. If you are using higher, it may be not changed because your solution will be here will be 0, 0, 0. That's the thing that you can see. But then if you are using in the very small parameter, that will be not happen. So there will be significant values there. But then the issue would be yeah, there will be an issue because of what? Because whenever you use higher scaling factor, yes, that will be the issue. The time consuming, the time complexity will be very high. So that is also not good for a cryptographic algorithm. Okay, so that's why the normalized value should be in the good term. Okay, how you need to know your good term is depends on your solution letter. So you check your solution, how many digits are there. Okay. Okay. So I think you can answer my question, then you pass your exam. Okay. Okay. So in this case, we're going to run for today's tutorial. So I want you to do first. Try to play around, and then we will see. Okay, so the next one I'm using for secure communication. I'm using a text, and it's just a very simple method. I just saw that value of kinetic sequence with our plain text. Okay, so the advantage is also very efficient. It is lightweight computation, so it's doesn't occur higher computation, and then very high sensitivity, and then it's robust security, and also our scalability is very good. And then where we can apply this method in secure message, in IoT network, in blockchain transition, and also in military communication. Okay, so let's say we in the peer-to-peer messaging, we want to a device A wants to send a confidential text to a device B. So basically, if previously in Julius Caesar world, they are using just a paper, so they give the ciphertext using the birds, and then they will encode the message. Then they will have, I mean, for example, you want to write attack at dawn, but then you're not writing it so that everyone can understand. So in that paper, the general will read and understand what they have to do. So nowadays, peer-to-peer messaging is very important for confidential text, especially in military. So we want our message to be encrypted when we cross the channel, when it is in the medium of internet, so that it will be very secure if there is an attack in the middle. Okay, so how we want to do? First, we design the same one. We define the input. We give the initial condition, the parameter, and also the length of the plain text. So this is also important. Then, because we want to generate, I mean, if you have a long text, then it will be a bit long. So, and then we generate the chaotic values. In here, I'm giving the example of using the 10 map. Okay, so this is a 10 map. You have U parameter. I think maybe this is the first time. Maybe a few of you, we have a mu and x only. It is very simple. The 10 map is very simple, but then quite interesting of the analysis. And then we scale and we normalize, and then we encrypt. We using SAW, but then before we encrypt, we need to convert to ASCII. So in this method, we have to convert into ASCII, but then there is no issue because the computer can directly change between decimal to binary to decimal. Then we can have the answer. Okay. For example, this one, I'm sending attack for the original plain text, and then the sequence. The sequence that generate after the normalized value, this is the key, and then I store it using, I use the method of store to get the ciphertext. So the store method is also very easy, right? But then in this one, you have to use it in binary. So you can, maybe I can give you an example for store. So let's say here you have 65 as your key, and you should have your binary, and this is your key. For example, this is a plain text, and this is your key. So let's say so the store method is very easy for binary, whereby 1 and 1 only. So we will have the answer. So this is the answer for the ciphertext. But then here again, we need to change from binary to decimal. It's just a matter of your algorithm, how you want to give your ciphertext. And then, and this one, if you convert, we will have, here I'm written as 193. So I'm not sure. I think it's correct because I checked the binary when I doing the simulation. So that's why we have 193 here for 128 as a key, and 65 I think is A. Yes. So A in the ASCII is 65. Okay, so basically solve method is very easy using binary. So you get directly the answer. Okay, so maybe I would like to ask here if you are using, you reuse your key string for multiple message. For example, this is a message you are sending attack. So for the next day, you want to message to your general, for example, rest at down, for example. So and then you are using the same key string. So is it okay? So what is the reason? So we want to check the reason. What is the reason? Why is this not okay? So when we are repeatedly using the same key stream, so the pattern will be there. So it is very vulnerable for attack. Okay, so that's why repeating the same key is not good. So because we have the chaotic system, you just use, because there are so many solution there. So you don't use the same key, because then if you are using the same key, the pattern, they can use the frequency analysis to attack you, so it's not good. Okay. Again, just now we are talking about the scale, the normalized 8-bit. What if I'm changing to small or large? But then now my question is, why? Why we normalize our sequence? Why we normalize it? To?
Diffusion operations, because the text, because the plain text are in 0 to 255. So that and the random number generates from the chaotic map the real numbers.
Okay, so meaning that for compatibility to our computer system. Okay, for compatibility. So then we can compute. If not, it's very difficult to compute. Okay, so and it also ensure randomness and also usability. Okay, so normalize is very important step whenever we want to do the algorithm. Okay. All right. So next, this one still, but then I'm using a text, but then the method is substitution. It's very easy substitution. Algorithm that I'm using here is very easy for you to understand how we want to use chaos. Okay, so now is the substitution, and this one is Hannen map. Okay, it's a Hannen map. And why? Because the advantage, we have a simple, but then it's high security and also very lightweight. So the computational is very not high, so it's easy, and the time complexity is also very good. Okay, and then where we want to apply for the password management, for secure text storage, and also for offline encryption. Okay. Okay, so in this case a bit different for the encryption only, because we are using substitution. The same method we will going to produce later. We define, we generate, we solve, and then we generate the sequence and we normalize. But then in encryption, the method is different. We are using substitution mapping. Okay, so let's see. This one I'm using the password because I'm giving you the scenario. So actually for this scenario, a company needs to securely store a password in encrypted format. So this is the scenario. So let's say this is the password, and then from this original, we get the substitution. We get the chaotic sequence, we normalize it, and then we use the substitution method, and then we get the ciphertext. So in this case, it's not using binary, because substitution we can just directly use the mode 256. So let's have a look for the example. Here, it will be the same example actually. Will be the same example because A is 65. Okay, in ARC-C, A is 65, and our key, because I'm using the same what we call this, chaotic sequence, so is 1 to 8. So supposedly we're going to get the same result, which is 193, but then without using the binary. So we just simply use the substitution method whereby 65 plus with 128 mod 256. So you will have 193, right? So basically these two method will be not the same. There are many numbers that giving a different value, but in this case, coincidentally they are having the same. Okay, so in this case, we are using the substitution method to generate the ciphertext. It's a very simple result. I mean, it's a very simple algorithm. Just for sharing you how we want to use chaos in cryptography. Okay, and so the next is also for the transmission, but then I'm using image for this case, and the method is also a SOR, it's a simple one. And then the advantage for this one is for simplicity, but then we can have high security and versatility, whereby actually we can use both in grayscale or also RGB. And the most important, SOR is reversible, so we can encrypt and then we can decrypt. It is secure image transmission. It can be used in medical imaging. It can be used for the civilian and also for digital watermarking. Okay, so there are maybe in your particular problem you can mix a few methods in your algorithm, yeah, to get one. So this is just the example for one particular things, then you got the result. So actually in your algorithm, you will have mix of process of encryption. Okay, so for example, in this case, in this scenario, a radiology department wants to securely transmit an X-ray image to a remote specialist for diagnosis. So when they want to send the image through the channel, through the internet, so because this is a data, a patient data, so it should be confidential. That's why it's very important for us to encrypt, so that if there is any middle of the man attack, then they will not have something. So they will have a noisy image only. So in this case, after we generate the key stream, generate the sequence, then we use the encryption method SOR in each pixel value of the key stream. But then here is the step that is very important that we have to make sure is the dimension of the image. Okay, so this one, it should be same as our key. So if not, we're going to get the error. So in this case, I'm using the 10 map. And I have the original image of the X-ray. And this one will be our encrypted image in the noise. So if they get this image, then they do the analysis, they will got nothing. Okay? And then, yeah, of course, to make sure our algorithm successful means that our decrypted image should be the same as our encrypted image. Okay? Okay. So, right. Okay. And then I'm using audio. for just to share, this is very also very simple one. I'm using SOR and 10 map. Okay, so we will have a high randomness and noise like signal. If you are, and then of course SOR is reversible, and the computation is also not high, so it's very good for IoT and also any system for encryption and decryption, and also scalability. And then this audio basically in government, I mean in military, mostly all the data would be encrypted securely, okay, and they have the hardware, okay, they have the devices, encrypted devices for the military, to secure their data in terms of their message, in terms of their audio. So in terms of anything, they will have their hardware problem. But then, I don't know in other country, but then in Malaysia, the problem would be in each department. For example, like we have army, we have the navy, and we have the air force, right? So for each department, uses a different type of hardware devices, and these hardware devices mainly controlled by one company, whereby for each company they are not even integrate, meaning that if the main what we call CNC, command and control, for us we call it ATM, is the main what we call main government would like to send a message for all these three parties, it will be not accepted. Because this Navy and Air Force using the different type of devices, so if the CNC use the same devices, then they can go through. But then if the different devices, they cannot go through. So that is the main problem in, I don't know in India, but then in Malaysia, there will be this is the problem. So I'm working with the industry whereby they would like to have, because they have these devices, so for sure we cannot remove all the devices and use mine. No, now we are trying to adapt all these devices and then we have a main devices that can intercept for each devices that has been existed in military. So I would say that is our intention, but then I don't know how it goes. So let's see if you can develop and they agree, so that they no need to remove the old devices and buy a new one that integrate for each other. So they just buy a new one for the command and control for everyone. Okay, so hopefully there is something. Okay, so for this example, I'm giving a scenario where a military operation requires secure real-time communication between field unit and command center. So the transmit audio contain sensitive tactical information, for example, which needs to be ensure the confidentiality and integrity with this audio communication. So that's why they need to encrypt their audio. So first, yeah, for sure we need to set up, and in this audio we use 16-bit, because 16-bit is the suitable bit for the audio, and then we generate the chaotic sequence, and then we normalize the sequence, and then we have to check the dimension, and also then we can use our encryption SOR method. So this is very simple. You can just generate for any video. This one I just taking any audio in YouTube. I don't know any sounds. I just take any sounds that makes like piano sounds. I'm trying. No, the thing is I put the sound, but then I don't know how to play the sounds. Yeah, actually I don't know how to play the sounds. I put the sound, so I don't know how to play the sounds. That's the problem. It's not coming, right? Anyone knows how to play the sound? So basically this is, maybe I just press here. So this is the example that I'm using, just the piano sounds. So this is the noise. Yeah, as you can see from the start will be the noise, and then when I decrypt, we have the same sound again. So this is, I'm just using the SAW. It's very simple method, but then yes, even SAW is quite tedious for the code because audio kind of difficult. Previously, I have done with what we call intermediate variables of the chaotic sequence. So I'm using intermediate variables for encryption process. So it's more tedious. So I can bear with the SAW one. So that's why I can show you. Yeah, because I'm just preparing during this lecture. So I've never done SAW method for audio for sure, because it's a simple for sure, right? So, but then, yeah, that is what we have. Okay, so the next is the concept. The next is the concept, whereby in cryptography and IoT, you have the key generation. So you can use for encryption, we can use for transmission, and then you can have your original data. Okay, so this is basically the overview of the cryptography in chaos. And then in IoT, we have the, for example, if you have the smart home, we want to encrypt our data, for example, temperature data, and then we want to have a secured camera view. And yeah, for me also, I have the CCTV in my house, but then for sure it's not even encrypted. So if someone can attack my apps, for sure you can see my house. Okay, so there is actually, I mean, there is one more maybe for your future direction, whereby you, because this is IoT, right? You need to have a very low computational method. But then when you, for the video, especially when we talk about video, it's a bit complicated. But then there is maybe one of direction that you can go for to secure your, smart home in any way. So then it can be connected for each other. Okay, so I mean, this is one of the things that you can be done, and you can, I mean, there are several, for sure, they are encrypted. They are saying they are encrypted, but they're not into depth, for surely. Maybe the encrypted is only for the password and the username for you to enter the apps. That's all. So that's why we call it encrypted. But then into that, there are video, there are anything that been stored in our devices, because, for example, in my apps, I can check 2 months of my, 2 months period. So, it's long. It's a long for you to what we call, to check the pattern of me and my family, right? So you can have something, you can analyze something there. So that's why this is also a few direction for you. But yeah, of course, video is complicated, maybe, but then if you go into this interest, then you can go. Okay, so this is the concept, and I'm sharing you one more thing. I think I'm not have enough time for hash function. So hash function also we can do something with chaos. Okay, this one I'm not trying. I didn't have any research for hash function in chaotic. Okay, so it's very efficient because slight change in the output will come up with a different hash value. So each hash value will have a different value. Even like, for example, you are sending hello, hello with H big letter. If you have time, I will also discuss with this in the tutorial. But then if you change hello in the small letter, your hash value will be very different. Okay, so that is the best for chaos. And then you will be very difficult to find two distinct input on that such. Okay, and then if you are given this hash value, if you are given this hash value, it's very impossible for you to get the input. Okay, this is the hash value, so it's very impossible for you to get the input whenever you use the hash value. Okay. So how we want to use this? We input the text. I'm using the text here, and then we normalize into 1 and 0. So for now, this case, you normalize your text. Okay. Previously, we normalize our chaotic sequence. Okay, and then we generate the chaotic sequence, and then we combine the input and the chaotic sequence using mode 1. Okay, we're using mode 1 in this particular algorithm, and then we can generate the hash. Okay, so the usage of hash is very big. It can be in data integrity, in cryptographic protocol, password storage, and blockchain. So I'm sharing this one because of what? As I mentioned, in your algorithm, you should include few of methods. So hash function is also one of the methods that you should include. Okay. So I think that's all. So this is the conclusion. I'm giving you the conclusion. Yeah, efficient, lightweight, high unpredictability, scalable, and also flexible. But then one more thing that you have to remember is also the limitation. Okay, chaos also encountered the limitation. Okay, so often chaos introduce slight computational delay. Okay, so this is often that happen to us, the delay, and in IoT application, this delay is very critical. Okay, it can impact so many, and the IoT can suffer from the performance degradation. So with this delay, you have to do something. So this is one of the solutions that I'm sharing. We can optimize the algorithm for faster key generation, or we can pre-compute key stream. So means that we compute first the key generation before we start for our algorithm. Okay, and for this one, the limitation is, IoT, we include so many devices, maybe 1,000, maybe millions. So managing unique chaotic key for every devices is actually complex. Okay, so impact the larger network will face delay in distributing this key. So because for each one you need to compute different keys. So this managing unit managing the key will be very complex. So maybe the solution you can have the chaotic hierarchical key management system. So this is still pending. This is what I mentioned. The IoT network still pending. So maybe you can do something with this soon. Okay, soon. Soon. So means that try to work something if you are interested in cryptography and chaos. So I think that's all from me. So any question? Yeah.
Are there any standardized cryptographic algorithms based on chaos theory like we have AES, DES, RSA? In that fashion, do we have any standardized algorithm?
No, no, there is no standard algorithm for chaos. So you create your algorithm.
So, ma'am, how do we start by thinking on the pattern that I want? Let's say I want to create a chaos theory based algorithm. So,
No, no, there is no standard model. You just focus in base. First of all, you just define it.
No, no, he mentioned like RSA, you have the standard procedure
so let's
too.
RSA is something which has been given by NIST, AES which has been given by NIST. It is, I mean, a standardized algorithm which is given by NIST so that everybody can use that. It is given algorithm by NIST. So I was asking whether are there any standardized algorithms
No.
based on chaos theory?
No, there is no. There is none. In fact, I'm trying in my country we have a cyber security we call it cyber security Malaysia. We are giving algorithm for them to verify, but then still impending.
So ma'am,
It's
let's say if I want to come up with an algorithm,
yeah.
then what should, how do I start about it? I mean, like you took few initial conditions like canon map and so on. So in your opinion, what would be a good chaos theory system which should be taken so that it can be deployed into IoT system?
So it depends on your what we call your intention. So for example that I'm giving just now is for the key generation. So you can have your key, and then I mean chaos system can give you a key generation, so you can produce the key for the algorithm. So it depends on it depends on you how you want to design your algorithm. So designing algorithm is also one of the things that you need to be done.
Ma'am, so like if we come up with a new, let's say, cryptographic algorithm, what we do is we check it via a few automated tools against various attacks. Like a well-known tool is Avispa. So are there any tools or are there any checks if we develop a cryptographic algorithm based on chaos theory? Are there any automated tools available to check that, or we have to do it manually?
No, we have to do it manually. So there is no tool. But then in cybersecurity Malaysia, that's why they're still pending, because they don't know how to verify and how they want to do the cryptanalysis. So So that's why they didn't find the way to solve, to check whether my algorithm is good enough for a standard. Okay? So, yeah.
Can we use this to generate asymmetric cryptography keys?
Asymmetric cryptography? Yes.
So, ma'am, won't that make it easy for us to generate asymmetric keys rather than just generating symmetric keys?
Asymmetric a bit difficult. Asymmetric a bit difficult because you can manage to get in one algorithm, but then one data, but then for another data, you will have, with the same algorithm, you will not get the result.
So, like you mentioned that distributing keys would be a problem in a large scale IoT network. So, if we generate the asymmetric keys at just the first time, so won't that will make it easy?
No, I didn't get it.
Like you mentioned here that in a large IoT system, distributing keys via chaotic system would cause a delay because the key generation process takes time. So if for just once make sure that when a system is initialized, we generate the keys, asymmetric keys just for once, won't that make it easy?
For if you're doing for once, and then for what purpose you are creating so much difficult in terms of algorithm, but then you just want to use for once. If you want to use for once, for sure you will have the result, but then there is no use because to do it for for one only data, but then you cannot use for the other data. So
It can be used for other data because if asymmetric key will be generated only one time, my public key would be available to everybody. My private key will be only private to me.
yes,
Anybody can encrypt using my public key and send me the data.
yes, yeah, but then that one can be, but then when you have the data, when the data comes in, maybe your algorithm didn't fit into it. It can be asymmetric key using chaos. It can be done because you use your public key and you share your, you use your public key and then you share your public key. It can be done. But then for the data to come in and to get the encrypted, is it still fine? But then for you to decrypt it back, it can be difficult. For one data, maybe it's possible because you are trying with this data, but then if you change to another data, that will be very it can be. It depends on how is your data. So I try also with the asymmetric key. Yeah, that's happening. Of course, when we use the data, for our trial, we have a few datas. For example, I have a set of 10 datas. So few of it successful, but then another few of it is not successful because maybe the dimension is not the same. There are tedious things actually that makes the encryption and decryption fails. Okay? So anything else? Okay, if not, I think we would like to start at 2:10 sharp because I have a program with my, if you meet